So good morning, everyone. So we have an exciting session today on wide area networks, which talk about networks throughout Earth and also in the sky. So our first speaker is Sharad Agarwal, who's a senior principal researcher at Microsoft, where he's been doing networking research for 18 years. In addition to 40 papers, his research has impacted Azure, Windows, and Windows Phone. He's an ACM distinguished member. So Sharad, please take it away.
Thank you very much, Sanjay. Thank you all for being here. So I'm going to tell you about a research system called TIPSY that we are now running for the Microsoft Azure Global Backbone. This work is with Michael, who was our intern. My name is Sharad, my research colleagues, Rodrigo and Ryan, and our engineering colleagues who run the Azure WAN peering infrastructure, Jenny, Irina, and Somesh. Let me start by telling you what this work is about. A bunch of prior work has focused on content delivery, such as CDNs, web search results, social networking. In those applications, the performance of traffic egressing the cloud matters a lot. When a peering link experiences congestion in that egress direction, existing systems such as Espresso and Edge Fabric can be used to move it to an uncongested link. But Ingress is much harder because the cloud is not in direct control of which path a remote sender uses to send traffic to the cloud. So how do we ensure that traffic does not ingress on a congested peering link? For an increasingly important class of enterprise applications, the performance of traffic entering the cloud matters a lot. For example, when an end client is streaming up video to the cloud for video conferencing or for AI and ML pipelines. So what is a network operator to do when they experience ingress network congestion? There are a few different techniques that they could use to manage that. So let's talk about each one of those. You could change the DNS results to point to a different IP address that is not available on the congested ingress peering link. But this requires you to wait for DNS cache results to expire. BGP tricks are notoriously hard to get right because policies out there inconsistently treat them. You can withdraw the BGP prefix on the congested link while continuing to anycast it elsewhere. This provides immediate relief on that congested ingress peering link, but you could push the problem elsewhere. This is the problem that we solve in TIPSY. So our system TIPSY predicts where traffic will ingress the network, even under hypothetical prefix withdrawal situations. And this allows us to move flows in a safe manner. Let me make the problem more concrete with a real example. Here is a simplified topology. There's a sender, a remote sender somewhere out there at the very top. There's a destination server inside Azure at the bottom. And as is typical, reachability for that destination is advertised in an anycast fashion on all the peering links, as shown in those green lines. On January 4th, 2022, at 2100 hours, the peering link I1 on the far right with 400 gig capacity hit 90% utilization in the ingress direction. Now, at this point in time, TIPSY wasn't deployed. So the existing congestion management system withdrew the /10 anycast prefix at I1 that covered D. Now, this system would use to do this blindly in the hope that everything would work out. And sometimes that is indeed true. But in this case, that was not. So when it issued the BGP prefix withdrawal at I1, it immediately provided relief on peering link I1. Utilization dropped to safe levels. However, I2, that also has 400 gig capacity, then exceeded utilization. So the mitigation system then kicked in again, issued another BGP prefix withdrawal. Again, I2 dropped to safe utilization levels, but then I3, now with only 100 gig capacity, exceeded utilization. The system issued a withdrawal there, then I4 also exceeded utilization. It issued another BGP prefix withdrawal. Eventually, traffic spread to enough places that everything was fine. So let's think about what's happening during this time to traffic. There's packet loss, there's excessive congestion, and each time a withdrawal happens, it takes some time for traffic counters to update, for the congestion management system to notice and react, and then do additional withdrawals. And in this example, ASB is a large telco with direct peering in over 60 routers in over 30 different geographic locations. So there's considerable uncertainty as to where traffic will arrive each time a withdrawal is made. And we have similar examples where multiple ASs are involved instead of just one neighboring AS. Now, if we knew from the very start what would happen for every BGP prefix withdrawal, we could do one of two things better. We could either pick a different prefix, where if we were to withdraw that, that would resolve congestion with just one withdrawal, or we could stick to the original prefix and issue multiple withdrawals at the very same time, thereby minimizing the window of congestion. The punchline is that in post-incident analysis, TIPSY correctly predicted the outcome of every action here, as well as in other similar incidents. So why is it so hard to predict where traffic will enter a wide area network? You have to remember BGP paths are not symmetric. So just because I use a particular BGP AS path to reach a destination doesn't mean that destination uses the same path to reach me. But really, the crux of the problem is that we don't know how our route advertisements get selected and propagated by routers that are foreign to our network. And those policies and topologies are continually changing. Another reason this problem is hard is scale. If we have only 2 peering connections, guessing which one traffic comes in on is pretty easy. But if we're the Microsoft Global Network with tens of thousands of peering connections, this is much harder. And this is not atypical for a large wide area network. So let's talk about our approach. At a high level, what we do is we build a predictive model. So given a set of peering links for a wide area network, for a given traffic flow that is entering that wide area network, produce the top K predicted links that are most likely to receive that flow. In production, we use a K value of 3. The key point here is that we are not predicting the entire AS path. We are only predicting which ingress peering link that traffic will arrive on. To train this model, we primarily rely on sampled flow data with some additional annotations. These annotations include what is the source AS that owns that source prefix, what is the geolocation for that source prefix, and similar information for the destination that is inside our wide area network. We also use information about all the peering interfaces that we have, which AS it peers with, what is the physical location of that peering interface. So we designed our own statistical classification algorithms for TIPSY. Our goal was to achieve high accuracy at low cost and high inference speed. As such, all the models require only one pass over the data. We have multiple models, and we use them in an ensemble. Models that use more specific features are essentially memorizing. What happened to a specific flow in the past is exactly what will happen to that flow in the future. Models that use less specific features allow for more transfer learning. If a flow A looks a little bit like flow B, then maybe what happened to A is what will happen to B. For example, the model in the leftmost column that uses source prefix as one of those values is very specific to flows with that same source prefix. But the model in the next column that uses source geolocation is more general to all the flows with the source prefixes that are in that same geolocation. So in our ensemble, we first use a very specific model, and then with lower priority, use a more general model, and thereby get the best of both worlds. So let's look at our overall architecture at a high level. So there are ASs out there. They peer with us at peering routers. Those routers are sending flow information to a flow collector. And then we do a whole bunch of processing. Now, this flow data is ordered tens of terabytes per day for our wide area network. And in production, we process 3 months of data to build one model. So we are processing petabytes of data. For all of our learning, we rely on a Databricks cluster on Azure. We expend 544 cores with an aggregate of 4 terabytes of RAM, and we're using Delta Cache accelerated nodes that have high throughput NVMe storage. So I talked about that congestion management system. What it's doing is it is periodically looking for congestion events. When it identifies a congestion event, it sends to TIPSY a candidate prefix withdrawal that it wants to make and the set of flows that could be impacted. TIPSY returns the min-max likely additional traffic load on the other peering links if the congestion management system were to do this withdrawal. The system is then going to decide, based on those values, is this a safe withdrawal to make or not? Is this going to cause additional congestion on other peering links? This part is still being finalized. If it does end up being safe, it is going to issue that withdrawal, and then that is going to mitigate congestion. Now, this picture is grossly simplified. There's a lot of other things going on that we don't talk about, such as authentication, orchestration of compute, and telemetry. OK, so let's talk about evaluation. Our methodology for evaluation is the following. We first train TIPSY on past flow data, and then we query it on new flow data that it hasn't seen before. So the output of TIPSY is for every single flow, what is the probability of it entering every single interface? And we compare that against the ground truth. So to calculate accuracy for every byte, was the actual interface that that byte arrived on one of the top three interfaces that TIPSY predicted? Now, for the results that we show in the paper, we do this accuracy calculation for a minimal of 3 weeks of training, which is very pessimistic for TIPSY. In production, we actually use 3 months of training, and ideally, we would use 1 year of data. So here are the top-level results. When considering all ingress traffic, TIPSY's predictive capability accuracy is north of 96%. But when considering only ingress traffic that is involved in an outage, where prefixes are withdrawn at a peering link, then the accuracy is north of 76%. This is just the top-line results. We've got many more interesting detailed results in the paper. So in summary, TIPSY predicts where traffic enters the network, and this is being used to safely handle ingress congestion events. If I were to make an observation of where we are headed with this problem, I would say that the business of running WAN backbones has survived because of statistical multiplexing. You run fat pipes in the center of the network that are 1,000 times fatter than the individual links where users are. And the hope is that not all the users will pummel the network at exactly the same point in time and overload those fat pipes. But this assumption may now be at risk from 5G. 5G in eMBB mode is promising end users 10 gigabit per second of uplink. And if you consider that many peering links tend to be 10 gig to 100 gig in capacity, could we soon end up in a situation where only 10 users synchronizing in time congest peering links even more frequently than is happening today? Thank you very much for watching. I'm happy to take some questions. And we are hiring full-time PhD graduates. So if you want to work on fun systems like this, please come find us.
Thank you.
Hey, Jun Kim from Princeton. Great talk. This is maybe just a clarifying question. You said like I2, when the example in the first earlier slides, you had I2, I1 for /10s, and you do the withdrawal. Do you just have a fixed set of prefixes like /10s, or do you also determine the size of the prefix you want to withdraw, like /24, so that you don't take all the way to I1 and just a portion of I1 and then do that?
Thank you for that question. Really good question. So we do rely quite a bit on Anycast, and whenever possible, we try and advertise large aggregates of prefixes so as not to pollute BGP tables out there. That being said, we do also do Anycast rings, where some more specific prefixes are advertised on certain peering links, while also advertising the larger block also on those peering links and everywhere else. So we do have a little bit of that flexibility, but it's not all the way down to /24s, because that would significantly bloat BGP peering tables out there.
Hey, Laurent from ATH. Thanks a lot for the talk. I was wondering whether you folks consider an alternative to your predictive model. So assuming you're not always congested at the ingress. So one thing I could imagine is if I want to learn what my neighbors will do when I send them a withdrawal, I can just actually do it, for instance, during the night, and then I can see how they will react to this announcement when there is no congestion, right? And so I can really do it, and that doesn't require any predictive model, right? Perhaps there is some operational constraint here. I'm probably missing that prevents this from being as general as your technique. But I don't know if that's something you consider at any time.
Fascinating question. Really great idea. I would say operationally, the challenge would be just causing BGP churn and worrying about what that does to our neighbors' routing infrastructure. And in particular, because we're running a global infrastructure, there's traffic coming in all the time. Even at off-peak times, there's sometimes bulk traffic transfers that are happening from customer systems. So it can be challenging, but what I would say is that one of the reasons why TIPSY works really well is we learn from past situations where even potentially congestion is not what happened, but rather a peering link outage happened. It could have happened due to a maintenance window or somebody unplugged something. And so that is a natural prefix withdrawal event that happens, and we learn from that. And so if you look in the paper, we do have some tables showing how often those natural events happen and how TIPSY, the longer you train, the more of those events we actually catch and learn from.
The last question.
Hi, Mark Handley. If somebody was wanting to be malicious, could they send you a ton of spoof traffic and retrain TIPSY?
Awesome question. I love that. In fact, one of the things that we briefly touch upon in the paper, but we don't really talk about much, is we were looking at these corner cases where TIPSY wasn't providing really good accuracy. And we're scratching our heads like, well, what's going on? And then we realized TIPSY was identifying situations where traffic should have come in on certain peering links, but it wasn't coming in there. It was coming on really unexpected links. For example, we saw traffic coming in from US National Labs at a peering link at an exchange point in South Africa. And we knew for a fact that those labs did not run a global wide area network, so there should be no legit reason why traffic from them is coming in from that South African exchange. So that was a clear indication to us, at least, that this potentially is spoof traffic or attack traffic. So I would say that there's good potential for using a system like TIPSY for being able to actually catch these types of spoof traffic. And maybe there's a way to work that in such a way that we don't learn from those situations.
Thank you, Sherwood. Let's thank the speaker.